Okay, so welcome everyone to this new episode of EagleFly, the experimental debugger. Today we will continue making this awesome debugger, and if you'd like to follow along, please don't hesitate and be welcome. If you want to ask some questions, please post them on Twitter or YouTube and I'll be there to answer. With that said, let's start by opening the project. um, the last thing we did, if I remember correctly, because I don't remember totally, was that, well, yes, I do. We were finishing with the REX prefix disassembler, so that if we run the test project, we're playing around with REX prefixes and some special situations that the encoding itself happens to have. So that you see here, we have some bunch of addressing modes here, and as well, while we were doing RBX, we added the functionality for SIB stuff and stuff like that. So that we should know, like, hey, how does everything there work, and we pretty much constructed both things at the same time, because, well, that's the way it went, So yeah, so if you see here, everything seems fine. Now we have these particular things, for example, these zero displacements, that even though this is correct, because the encoding itself has those displacement encoded into the instruction. If we go to the instruction stream here, and I don't know if I say instruction stream, yeah, you see here, these are the instructions, and you can see here this 0x00 thing at the last thing of the instruction, which is, it's mandatory, it's just like a mandatory prefix, but this is a suffix, let's say. It's our mandatory suffix for this particular addressing mode, since we're using RVP as a base, we need to use 0000. If it was EBP, it will follow the rules that we made before, for the addressing modes. And probably that's the next thing we should do, for EBP and stuff. Now for handling EBP, we have to have 66, 67 address size override. So yeah, that's something that we also have to do, of course. So but before doing that, I just wanted to mention, like, hey, we have these particular ways of encoding. Another one, it could be this R13 here, used as an index, and yeah, those are it. RBP, R13. So let's think about this in a moment. Just before, this is the last thing about REX prefixes, so we should close up that today. So you can say that we are pretty much done for REX prefixes and stuff. And yeah, So let's go back to the ISO, and pretty much we just I just opening where we left off, which is this little table that tells us about these special cases, you know. And our job today has to be specifically with this thing, you know. And probably we can do as well this one, but this is another case. So the special cases that we encounter on this one, for example, on R13 or RBP, these two hold this special case where on the base, when you encode 101, which is EBP, the base register is unused if mod equals 0, you know. That's the normal thing that happens. Then the base register depends on mod encoding, you know. REX prefix adds a 4. This is all in compatibility mode, you know. If we are not in compatibility mode, then we shouldn't care. Okay, so there's some stuff there in the code that right now we haven't like specifically say like, hey, this is for compatibility mode or something, you know. So we should do that as well, you know. So this requires explicit displacement, so that pertains to the encoding itself, you know. So it's more like an assertion, let's say. You know, we can handle that as something that we can assert, or we should at least, you know. So let's go to fetch memory. And let me see here. This is the stuff that happened. And let's say, well, we're not gonna need anything of this, isn't it? So everything seems to be fine. so that's pretty much it. So here we can say, well, this particular field so this doesn't happen if we are on the other mode, you know. So this is Now this was because my question was like, why did it work in the first place? So let's go and see. We have an 8-bit displacement, which is because the math was not 0, okay? That was the reason why it didn't complain at all. Oh my god. Okay, it's a little bit weird. RBP plus RAX times 4. We cannot see C by at all. We're on 48. That's correct. And we have R13 plus RAX times 2 plus displacement, okay? Now we have RBP plus RAX times 2. And that's the same case scenario. Okay, now this is instruction that we have a 48 here on the 4th. That's correct. There you go, the entry is the same. Move. So let's see what happens. We have an invalid displacement. And here we were expecting it to be, you know, we have a mod equal to 0x0. And since this is the, well, let me go here. We have REX times 4. So yeah, I mean, that's not really true. I mean, if we can do this, that doesn't mean that it's just on compatibility mode, you know, because we are not on compatibility mode at all. Well, probably that's a little bit confusing, I think, because that's not the thing at all. I mean, if we can encode this on the IA32, I mean, that would be that it run the instruction as compatibility mode. That doesn't make sense at all. Yes, we do have a mod that has a displacement as that way, because that's what we wanted to show, you know, that's what we want to see, and it was possible to do that. In fact, we can see on the assembler. So yeah, so probably that's wrong, because if you see here, that's the problem, you know, it's not gonna enter, we're not gonna fetch it, but indeed we're gonna fetch it, but we shouldn't, because we don't have a base. And then it's like, hey, we have an RBP, but we don't have an RBP. Then you have a plus, and everything is just gonna be bananas, you know. Because now CBAD will be on a displacement, you know, 0x00, which is the displacement. So yeah, so that's totally wrong, and we can test it, you know. Let me just, so this is not the case. There you go. So yeah, this is REX stands for plus blah 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 blah, which is something that we encoded on the test assembly, if you remember. We have REX stands for plus displacement. This is the thing. So it is totally valid on IA32, you know. We can use REX, which we will need an REX prefix, you know, to use effective addresses that use that. So we have a 48 there. We are not, in this case, we are not using any RBX thing. This is using the SIB with the case of the mod equals 0 and using EBP as the column. So that gets us to as special cases. So REX stands for this 32, you know. And in fact, well, let's run it with dumping. So we just make assertions there. So here you go. This is REX stands for plus displacement. We have a 48, 8B, 1C. 1C means that we have SIB with RBX. 85 means that we have a scale of 4 with RAX, and okay, that what? Yeah, I mean, but this is not the mod equals 0. Well, it is, but I mean, it's not respecting the rules of this, you know. So even though it needs about it, yeah, well, that's it's kind of weird, you know. I was like, well, we're getting on to the place that what's the exact representation of it, you know. This is REX stands for 44. I mean, this is the thing, you know. I mean, we're looking at here with a real disassembler, and the real disassembler, what it's doing, you know, we have a scale index plus a displacement. That's all, you know. We don't have a base, so we shouldn't compute the base. So that respects REX or EAX or any kind of addressing mode. If we would like to choose, let's say, because remember that the mod is in the mod RAM, not on the SIB. So the SIB is totally different. This is respecting the rule of the mod, you know, because we're on the mod saying if we have the mod of that, then we have a displacement 32 with no base, you know. If the mod was other thing as the other as the other streams, you know. So pretty much here we are testing different ways of the mod, you know. If the mod is, for example, this is if the mod is equal to 0, we have this. If the mod is equal to this is 1, then we have this, because this is an 8-bit displacement with RBP as a base, you know. If we have 2, which is this case, then we have RBP and displacement 32 and RBP, and this is the scale, this is independent, this goes on the SIB. And then if we have R13, then this is the same way. This is the same, just using 49, you know. Then we use 49 and we get it on the base, you know. 49 we get R13, and the same goes as well. So yeah, I mean, that's the only, I mean, we were doing it correctly, just I was like trying to think like, are we doing it wrong or something? Or are we misunderstanding the idea behind it? It's just like, I mean, it's they don't explain it. They don't explain it too good, you know. I mean, how it does. I mean, the problem that they have is that they don't explain thoroughly the relationships between 64-bit mode and 32-bit mode. So you have to pretty much guess like that most of the things are gonna work pretty much the same way. They just extend these little things about in 64-bit mode, you know, like, oh yeah, we have we can use these extended prefixes, but pretty much that's the only difference, you know. I mean, the only difference is that we can extend the registers to use through R8 through R15. That's all. The other things pretty much respect the same idea, you know. And normally, you know, if you have an address prefix of 4-bit which is not decoded, And yeah, you know, in REX prefix as a 4-bit on the base, but yeah, I mean, this should be the thing. Now, for example, this one, which also SAB, this is the other case. Whenever the index is equal to ESP, which is not possible normally, you know, index register not used, ESP cannot be used as an index register. That's something we know for sure. REX prefix, that's a 4-bit, which is decoded, and that's something that we do on the code. We tested out on this one. We cannot use ESP, but we can use RSP, you know, and that's something that we did on the disassembler with this one. RSP plus R12 times 8, you know, we use RSP, and then we use R12 as an index scale. We can also use R12, you know, which it will use it as a base, you know. This is kind of interesting the way it does it. R13 the same way it goes with this. Yeah, and we do it here, you know, if SIB byte is equal, this is all the checking for if we have data size invalid in there, you know. So yeah, I mean, I don't see why this should not be the case. With all the cases that we've been through, we can just add more cases, you know, like, hey, boom, 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 if that's the case. But I think pretty much this is the way to go, you know. Yeah. So yeah, so we check this because we handle this. We check this because we handle this. Now let's go for the mod ramp by and see if we do this as well. You know, the mod ramp by if the mod equal to 0 and the RM equal to B101, that means that we are on the RM using the base field for it, and we try to encode EBP base register not used. This is the case for this one. We are not gonna have a base register of EBP without displacement must be done using mod equals 01 with displacement of 0. That's something also that we checked, you know, because of the use of R13. This is something that we also, well, if we don't assert it, we can do it, you know. I mean, we can add those assertions somewhere. And if not, well, we should think about something different. And that's because if we want R13, which is this case, we need a displacement. And we have data size 32. So yeah, I mean, I was like mentioning like, well, that's pretty much a warning for, let's say, assemblers, because if assemblers wanted to encode, let's say, that instruction, they have to respect that idea. Of course, if we want to go and say, well, we want to disassemble that thing, uh, if somebody gives us something that it's totally bogus, well, we're gonna, the disassembler, the worst case scenario is that it's just gonna disassemble garbage. I mean, if the code stream is just doing something that is not correct, let's say. So in that case, the worst case thing is like, well, you didn't encode it with that case scenario. We can just assert as well, if that was the case, but we cannot say because it can also be valid, not because they wanted to encode R13, but because they want to do something different, they gotta encode a displacement 32 or something like that, They are just like, yeah, there are special cases for the encoding, but they are not special cases for the disassembler, if that makes sense, yeah. Yeah, we gotta follow the idea, but that's all, we there's not a lot more to do that, Yeah, so like, I'm gonna put here now, this follows, yeah, 32 and x64 addressing modes, special cases. That's it. So now we handle it correctly, and that's something good to have, So yeah, we know that this is also not possible. If you want to do it, yeah, we have to go the other way. And the same goes as, even though I mean, if we want to, let's say we want to encode move RSP RBP, we're gonna have a special encoding there, We have 48 AB. We got 65 because there you go. We have a mother M, and we have a 00 displacement. That means that we have an 8-bit displacement, because that's necessary as well, So this thing is just respecting that rule. The assembler is respecting that rule, and we're just like following the same idea, We have a mother M, but it's 65, which is this one, and we have RSP, and we have RBP plus displacement, which is the case. And then what else? If we wanna get the mod different to 1 and the RM is gonna be B equal 100, the SIB byte is gonna be present. Yeah, we're going for ESP. SIB byte required for ESP based addressing. We're gonna go with ESP based, we gotta go and do that. REX prefix adds the 4-bit. So what happens if we want to do the other one like this? since RSP has to be on the SIB, it's just gonna go with the SIB, you know, because that's something that he can do on the base. So we see the base. Oh my god. This is, yeah. So this needs an SIB, but then now we don't need the displacement of 0. In this case, we can just go pretty straightforward and say, yeah, you know, we have 48. AB, we have 2C, which is on the first column, which is just telling us that, yeah, we don't need a displacement. We just need to go for the SIB, and we have RBP as a register there. Then on the SIB, we see that we have 24, and that means that we have RSP as the base, and we have nothing as an index, you know? Yeah, so that's pretty much it. We have here 24, you know, and the SIB we have 24 as well. Now we have 2C and 24. Okay, good. So we have 2C and 24. Yeah. And then what else? So that's all, isn't it? Those are the special cases, which is kind of normal, you know, because that's something that we already checked, you know. We already know that we have to go for the SIB. We already know that we have to go for this. I mean, the encoding gives us that thing. If the encoding doesn't give us that thing, then we should assume that it's just another encoding, because it's not possible to have that thing. So we are running with the idea, the assumption that the encoding is correct, you know, that the encoding is something that it can be run and execute the instructions that we can use. Of course, I mean, probably that's not totally the case, but you know, I mean, we are on the early stages, and we cannot like say that we are gonna you know, there's some disassemblers that they do that, but they don't do it. I mean, they don't do it automatically. They do it, I mean, because the disassembler doesn't know what the stream should do, you know, at least semantically, you know. That's a little bit more hard for it to understand, which is something that, you know, there's something like semantic analysis and stuff like that they do, can try to analyze the code and see like, hey, what does this instruction is trying to do along the code section where it is working in, so that it makes sense that that instruction is what it's trying to do or something, you know, or whatever, which is a little bit hard to do, which we don't care right now. I mean, we don't care about all about that thing. So yeah, so if those are the special cases, well, we pretty much can say that that's the whole thing. So let's see now. So that's it for the SIB thing with X and with the base and the scale and whatever. That was a good thing. So let's try to do the last one. That's something good. And this one is gonna be a main opcode with the REX inside the you know, it's a main opcode with the REX field inside using REX prefix. We don't have anything of those, so we are gonna need to do the whole thing, you know. So that's good, you know. The only thing is that we have to find an opcode that uses that encoding. One instruction, sorry. So if we want to find those groups, I don't know. Where to find those. We know that, I mean, opcode extensions, that's something we do right now, but that's because they extended the opcode. This is the other way around. They are collapsing the opcode with the rec field inside of it. Use the OFOB opcode, use the 2 instruction, the OFB9 opcode, or the OFFH opcode. What? Okay, so this is an exception encoded. We have OFOB, OFB9, and OFFF. Yeah, we don't care about that. Some instructions use the same 2-byte opcode. If the instruction has variations or the opcode represents different instructions, will be used to differentiate the instruction. Okay, for the value of the mother and byte needed to decode the instruction. See table A6. There's an easy way. Well, yeah, this is common. That's the reason why we use the mother and byte, because we have opcode extensions. So that if we have the opcode using OF00, then all these instructions use OF00. Is valid or not invalid or not encoding 64-bit 4 through 4F are REX prefix combination when in 64-bit. Use FE, FF, group 4 and 5 for increment and decrement. Instruction is only available when it's 64-bit mode. we have some instructions that when in 64-bit mode, the instruction defaults to 64-bit operand size and cannot encode 32-bit operand size. That's something that we have to do as well. See an example of them. We have some of the data information there for in here, which are so these are the instructions. You know, they are the near jumps, and they are all the instructions that reference the ESP or the stack. Which they are jump instructions called leaves, pop, pop, push, push, red, push. Okay. Alright. Operand size forced to 64-bit operand size when yeah. Only exists on VX. We don't care about VX. 1, 2, and 3 by opcode maps. So I don't know where can I find one. Like literally. Fucking. This is the move. This is the fucking. These are the two floating point things. Right here we can find one pretty well. We can see it here, I guess. We just need to find and this is for non-64-bit mode. So let's go for 64-bit mode. For example, yeah, look at this one. This is a pop with the rack inside. But this is on 64-bit mode. Well, let's find it out here. Probably a pop or a push, probably a push as well. Well, I don't know, it doesn't matter. And we have different versions because we have Popeye. Popeye pushes the whole set of registers onto the stack in this order. Yeah. This is push A, and pop8 does the other way around. Only that it doesn't pop all DSP. That's all we need to know. This is, there you go, we got to the point where we want to pop. Okay, this uses extended opcode. Pop register memory 16. Pop register memory 32, register memory 64, pop register 16, pop top stack increment stack pointer cannot encode 32-bit operand size. Cannot encode 32-bit operand size. Okay. Pop top stack into R16 increment stack pointer. Okay, so we can pop onto memory, or we can pop onto a register, which is kind of cool. I mean, you think about it. This is one of the special instructions that allows that it can that it can move data from memory to memory, you know, which is a special case in this kind of architecture. So if you see the pop one, it's something that for example, in this is using the stack that is in memory is popping it to another place on the stack. So it's just a pop, you know. And yeah, I mean, this is like the special thing about this instruction. And I was like, this is a side way. This is a comment. Let's say, I was reading Mr. Casey Muratori's blog post about. He asked a question about why doesn't recent architectures don't use an architecture, you know, a computer architecture processor that pretty much uses only memory instead of registers, which it would be, I mean, it will follow the idea of this instruction, just moving things from memory to memory, which, I mean, that pretty much makes sense, you know. And probably in the, before, whenever, and most right now, it makes sense more right now, because memory is some of the processors now have memory really close to it, so the memory the amount of time to pass to go and fetch memory, it will be pretty much lower, you know, than on, you know, before processors, or I mean, probably, I mean, this processor is just gonna be the same, and that's the reason why it's using the caches and stuff. But most of the time, you know, we have and that's the reason why we have cache hierarchies and stuff, you know, so we can just work along that kind of idea and work all the stuff in caches and then move it back to storage on memory. So that's the idea, but you know, I don't know why they don't do it as well. So yeah, so this is published to the 16 increment. This is on 32, 64. Gonna encode 32-bit operand size. That's true. We have pop ds, pop top of stack into ds, increment stack pointer. Increment stack pointer. This is an RW that, if you remember, is this thing. Oh, this is the thing. Indicate the lower 3 bits of the output byte is used to encode the register operand without a modern byte. That's what we are looking for. Okay. The instruction lists the corresponding hexadecimal value of the output byte below 3 bits as 000B. In non-64-bit mode, a register code from 0 to 7 is set to the hexadecimal value of the output byte. In 64-bit mode indicates the 4-bit field of REXB, and opcode to 0 field encodes the register operand of the instruction. R0 is applicable only in 64-bit mode. Sorry, RO. RO is applicable only in 64-bit mode. See table 3.1 for the codes. So this is the table 3.1. So there's something to understand here, and is that whenever we are not on 64-bit mode, our register code from 0 through 7, which is the possible encoding for 3 bits, is set to the hexadecimal value of the opcode byte. Alright, so the opcode byte plus a value from 0 to 7 is the value. Okay, in 64-bit mode indicates the 4-bit field of REXB. Sorry. Okay. Well, this is the same, isn't it? Oh, so that means that in non-64-bit mode, there's no way to encode a register inside the main opcode? For example, we can encode a byte register. This is a table that we raise in. A byte register, word or quad word registers, you know. Oh my god. And this is the same here. We have R8L, R9L, you know, byte word or quad word registers. So yeah, these ones, they need REXP. We know also as well that SPL, BPL, SIL, and DIL also need REXP to be there. And AH is not encodable. And the rec field is gonna be 4. So yeah, I mean that makes sense. And that's the way you dive. Well, yeah, because this is the same for 567, for 567. You have RSP, RBP, RSI, RDI on 64-bit mode. Whenever we don't have REXP, and when we have REXP, then we have SPL, BPL, SIL, DIL. And whenever we have zero, 1, 2, 3, 4, 5, 6, 7. So how do you oh my god, oh my god, oh my god, where are they? We need REX when using SPL, BPL, SIL, and DIL. So, well, let's see it, you know? It's like, well, why not? I was like, well, I mean, the assembler is just the best thing to see. Because, yeah. So, I'm gonna say that I'm gonna encode a pop instruction. We can even encode a move, I guess, and say, well, probably not, but SLP, no, how SIPL, how do you call it? SPL. So move to SPL, divide pointer R8. So this needs, and probably, well, just not to get confused, I'm gonna call this, I'm gonna say that I just want to see the pattern. There we go. So we just have an REX. We don't even have the W bit set, and we can use SPL. We just needed the REX at all, you know. So if we just need to have REX. We don't even need to have REXP to have SPL, and the ISA is telling us that we need REXP to encode SPL, which is kind of weird, you know. That's not true. It's lying to us. That's kind of weird. Look at this. I mean, I'm encoding SPL on 64-bit mode without REXP, and the ISAT is telling us that you need it. How in life is that possible? So he's like, oh, you know, REXP. Oh, okay, so do they mean when we use it on the RB? Oh, okay, I got it. I didn't understand. Okay, so yeah, if you want to do it on a normal thing like this one, yeah, you can do it that way, which would be okay. We have 40, then we have at 8A, you know, because this is 8-bit register thing. We're moving 8-bit operand in memory to an 8-bit register, and we are using the mother M by 20. Okay, so if we go to 20, we have that we are using REX and we are using SPL. Yeah. So that's a special case here. We can try to do that, you know, as well. Why not? Because we already have that encoding added, and it's just simple to do. So we have to have the REX, we have to have 8A. Oh, we don't have 8A, isn't it? So let's see, 8A, it's this one. I thought, so what we have, we have 8-9, 8B, 8-9 with R64, this is the one. We haven't gotten 8A, which is okay. It's valid on 64-bit mode, so yeah. So let's go for this one. It's gonna be 8A and it uses R normally. Okay, here is the modrem. It has to be 2 0, I believe. Yeah. Right. So let's decode that. Now let me copy this. I don't know if I already have it. It seems like. Uh, okay. Yeah, it's the same. Okay. So let's go for the 48A to 0. So normal case scenario, yes, we have an REX. We don't have an REXW in this case, so normal operand sizes are gonna be in case. Now that's kind of funny. Well, no, that's correct because we are using the operand size to SPL. So yeah, that's correct. Oh, and we don't have the instruction stream. Oh, okay. So let's add it as well. Alright. So this is it seems like a 1 byte thing. 8A, let's see. Is this one, which is using the byte. So yeah, so it's a 1 byte table. This one has a modern prison. It goes is this one, it's RM. That means that if first operand is a rec and the last one it's an RM. Well, is moving from memory to rec. Okay, so this has to be false. And the operand count is 2, register operand size. This has to be 8-bit, alright? And yeah, immediate size, invalid, mnemonic. This is the same, it's a move instruction. And the operation mode goes for 64-bit and 32-bit as well, isn't it? Oh, let's see. Yeah. We have valid on 64-bit mode and compatibility mode. So that's it, and I have to add it here as well. And here as well. So let's see what happens, alright? We get an entry, we have a mother and present, operation mode, there is a invalid, there is size byte, it's a move with a byte, okay? That's what we were expecting here. Yeah. Mnemonic name, move, yeah. We don't have anything about that. Okay. So if we go and fetch memory, this is, I believe, this is REX, so this is gonna be no problem, I believe. Mod RAM, we don't have a displacement, push string to buffer, SIB present, we have that, and this index size is 8. We have REX, that's correct. There you go. So we don't have no problems with that. Now probably here is the problem that we're gonna have. Effective operand size is gonna be 1 byte, that's correct. And the result, I don't even know if we have that on the table, isn't it? We can just see. We have a mother and byte. We're not fetching there on field. We're just going for the rec. We got the operand byte size. There you go on the rec. And it's AH. Okay. So that was that's correct. That's correct. If that was well, it's not correct because we're on 64-bit mode and AH is not possible on 64-bit mode. So that's something that we have to observe as well. You know, the table, the thing I was like mentioning is like, do we have SPL or something? We don't have it, isn't it? We just have AH, CH, DH, BH, and we don't have SPL. So we need to change that as well. normally this stuff would be the case, but since, let me see the table, SPL so we have these ones. So we have 4. Now the value, it's AH, so we have to say well, we have to put it somewhere, you see. They could be here. But then it would break the size of it, you know. So this is where the way they do it, you know, they have it on this row. Now, since I think they are the only ones that are special, no, because RSP is just the same encoding here. Of course, it's need to be there, so they can be treated just specially, I guess, and just been moved here. Or even, you know, we can move it to a special group here, you know. Or even let's move it here, so each bar just goes the same way. Well, it doesn't matter, I guess. The tables are just the same. and we can just say that we're gonna have I don't know how they call it here. They're uniform byte registers. Okay, uniform. I don't know if they call it that way, but we're gonna start calling them that way because they're, well, pretty sure we don't have like uniform byte register. We have a better name to it, you know. Yeah. Yeah. And in here, whenever we put it there, and then over here, whenever we do this, this is gonna be 4. And I believe that's all we got, I think. And now if we do that, we can say over here that if we find out that we have an REX by, and afterwards all this jumping, we need the yarn field to be just the same encoding. You know, we are using the same thing. We'll be using the same idea here with the rec and stuff. The only thing we want to make sure, well, that's problematic. That's problematic because, yeah, I mean the encodings have to be 4, 5, 6, 7. I mean that's for it, but we can do it whatever, however we want, I guess. I mean we need it, but if you just say find out that if the system stays C by if it would be AH, DH, AH, whatever, you know, on the low side,
Yeah.
we can just say, hey, what about just saying an offset equal no, how you call it here, we need the bit scan reverse, isn't it? So info offset and offset greater or equal 0, 1, 2, 3, 4. Then the rect group base doesn't stay rect groups plus rect group rect type uniform byte offset minus 4. So that's the simplest thing you can do, you know. No, this is REX by so let's see there. We got the main buffers, REX, then we have to fetch the register operand. We're gonna fetch offset with the rec, which is 4, assert, blah blah blah, and then the info offset is 0 and the offset is 4. That's correct. Then we have to say that you have REX by G by minus 4, and the rec now is SPL, which is correct. So yeah, we have with SPL REX. And the C by we're on 49. That's correct. So yeah, I mean, that was it. The other thing looks pretty much similar to the thing we had before. It looks pretty much the same. Alright, so that's good. So now let's go to boom, 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 boom. Okay. So let's go back to the pop one, because the pop can, well, has that information that we were looking at, which is that where is it? This is the value. We can say that we are forking. We are looking for, let's say, something like this. And which is encoding the register inside of it. Of course, it has to beat this one, but if we see the pop, where is the table here? So we are saying that we have a pop, and then we have well, pop can be 64, 32, or 16. Okay, and probably the push is gonna be the same, but I don't know. So let's see the push first. The push follows the same idea as the pop. So the push this is the push. The push, yes, it has RW, RD, RD, the same idea here, and it has a 6. This is for the extended opcodes of the push cases. When we have a 50 there, we have a push with RW. Then we're gonna push R64 in the same idea. It's valid on 64-bit mode, not encodable on there. Decrements, and this is let's say this is O. That means that it has the opcode plus RDR. That means that if we say push REX, what's the encoding of it? Okay, we have 0 because it's a 64 thing, and we can even make a list of them. Push RBX, RCX, and it follows the encoding, you know. But you know, yeah. We cannot encode 32 bits, so we can test that as well. And let me move this a little bit. So where is it? There we go. So this is the push, and we are looking for REX. The value of the rec field is gonna be 0, or 4, 5, 7, 6, and blah 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 blah. You know. Okay, so that it's 50. So if we go on the 1 byte map and search for 50, we have a push, you know, and we have REX, R8, and we have RCX, R9, or RDX, R10, RBX, R11. It all depends on the base registers, and R12, R13, R14, R15, RSP, RBP, RSI. And in the same row we have the pop on the other side, you know, REXA, blah 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 blah. So they use the same thing, you know. So yeah, we can do that. We are just pushing with the 50. Pushing with the 50. Because we also have FF, but that's from memory to the stack. This is not valid on 32, so let's see. I have a lot there. EAX, invalid instruction operands. Yeah, we cannot push EAX. We could push AX. Yes, that's correct. We can push AX. And if we look at the disassembler, both of them are gonna look exactly the same. Oh no, look at this. Well, no, because you need a 66 for that. Yeah, you need a 66, and going for IAX. And the reason is because a push instruction has a 64-bit operand by default, you know. That's something that it says here. We have push, push, push. This one is the one we're looking for. Push rec has a effective operand size of 64-bit mode. That's important. So yeah, push rec mem the same way. Push fs, push es, push immediate a, push immediate 32, push fq, and that's all for the pushes. The pops have the same idea: rec, fs, gs, fq, and rec mem. We have the move, CRDR, we haven't touched that yet. We have the loops, loops conditionals, RTRs, load the task register, load the GDT, the LDT, and the IDT, the descriptor tables, and the CXC, you know, jump conditional on 0 on CX, I guess. I don't know, yeah. Jump leaf. Okay, so this is a special group here, which is yeah. Yeah. So yeah, this has to have a 66 thing there. And what else can we see there? Push is gonna be a 50 there. They can be push and immediate, and we can push the segment registers as well, which all of them have a different encoding, which we can do as well. So yeah, let's go for the 50 RW and 50 RD. So if we want to push RSI, and then we're gonna push R8 as well. We can see it. This is a 56. That's correct. And the other one has the mother and has the REX prefix, you know, which is telling us about that. So we can say 4150, 4150, 41. 41 is, yeah, we have a base, but we don't have a W because we don't need it, you know. So it would be probably it's just uh, something extra, you know, that we can just say about it. So let's go and push that, you know, let's go and push REX. Let's go and push REX, you know. So for that, let's go to encoding, and I'm gonna say this, the tiny instruction 0x50. Alright, and for that, well, we will need to add it to the stream as well. It's a 1 byte thing. We can add it here. Okay, this is a push entry, and we wanna we want to say that we don't have a model RAM, we don't have that. We have operand cam, it's just one. It's 64-bit, and it has an invalid thing there. It has a mnemonic name. So I gotta call it, well, and this only works on 64-bit mode. Alright. Well, it also, well, I don't know about real address, but it works on 64-bit mode, and it's not encodable on it's not encodable on compatibility like a C mode. Okay. So pretty much the mode is the one that's gonna say that, you know. Which is funny, you know, because for these particular cases they are just the same thing, you know. It's just like, well, we're on 64-bit mode, or we are on what? If we're on 64-bit mode, yeah, depending on the operating mode. So it's like if saying that is size operating mode. If we do that, we can just have one entry, and that's all she said. Which, you know, is just a little bit weird. Well, it's the first instruction that we find out that has that kind of thing. Right? But if that's the case, well, we have operating mode 32-bit, you know. So yeah, because that's the way we are doing it. Okay. I mean, there's nothing wrong with that, you know. It's just like, well, you know, it can be that thing, but the thing we're matching here, the entry thing, just has that as the case. So yeah, and if you want 16, we need a prefix, you know. We need a prefix. It depends if it depends on the effective address size, you know, but that's for R16. The other cases are just the same. And yeah, so there is size operating mode, we don't have that. and this is not there. So we can just add this. Well, you can say that, and let's see what happens, you know. So C by it's 50, and we have 3260. We have an REX. We have get the money thing. Get mnemonic entry. We got an entry there. It's a push, that's correct. And we don't have a mother end, we don't have a rec. We don't have an operation mode, you know. We don't have anything, okay. We don't have an immediate size. Well, the operation mode is telling me that it works on both, and the operating mode is that thing, you know, operating mode. And so if we go into it, you know, if at the begin thing we're always extracting operands, whatever, you know, we're gonna have to go and fetch it, and then we're gonna say, hey, you know, we got the buffer, that's correct. We have an entry, we just return with nothing in our hands. You go and fetch register operand and say the same idea, we are not gonna have anything at all. And well, pretty much we push, well, we push a push. And the C by should be on the 40 now. That's correct. And pretty much we do the same stuff as before. Oh. Whoa. That's weird. Well, it disassembled the other stuff, but it just happened to. Do we have 50s over all the place? What happened here? That's weird, isn't it? That means that he got a valid entry. probably is gonna be, we're never gonna touch this case now. Probably it's because on the way we're getting the mnemonic entry, the hash table, the thing that it's not totally correct, probably. I don't know, we have to check it. But first, I mean, yeah, we gotta do that. But let me just first. Well, I want to see that because it's kind of funny. It's I wanna say. Well. There you go, we have 03 and now 0305, that's correct. So we got the entry, it's a nav, that's correct. And we printed out it, and now C byte is pointing towards 0. Okay. Now let's see what the mnemonic thing does. Entry index, entry invalid, get table ID, we have to have 1 byte. So table at, table ID is 1 byte. We have 20. So we are on the group 1, which is all the 1 bytes. Okay. And then we like make a shuffle or ramble values there. Which they don't pretty much Oh, there you go. We have a 26 and a 26. So does that mean that if we, yeah, that's because of the hash, isn't it? Let's do it. Let's do it. Let's say we have, well, right now we have 0, 32, is 26, right? Now I don't know how many they are. But it got to the same value because I mean, it's the same, but it just mask the upper bits. Yeah, the most significant bits. So yeah, we got to the same thing, and that's why we're pushing a lot of pushes there. So the hash seems not to be right, so that means that we have to do something better now, you know, and that's the reason why we are just printing pushes all the way around. So yeah, that's right, our assumption was correct. We just print pushes like crazy. Okay, so yeah, that's the next thing we're gonna do. Let me press the do there. Fetch entry. We need to have a more intelligent way to think about entries there. I mean, it's simple, but it's not sufficient, you know? It's not sufficient, and probably because the way we are hashing it is just not, it doesn't make sense. So we have to research, I mean, we have to make a little bit of research of how to hash things. That would be really nice. So get entry index Now let me see what's the value that we have there. 4096. So that means that okay, let it compile. That this value divided by, it was divided, no, it's n. There you go. There's a problem. There's a problem. One pretty easy way to do it is just like, hey, if it's a 0, we don't care. But still, I mean, it's not just the 0. It probably there's a lot more entries that probably we're gonna have that problem. So doing the hashing for that thing, I mean, it's gonna take I mean, it's gonna take its own time when we make the archive and the file system to retrieve the tables. You know, all that stuff has to be done in that moment. All right. So yeah. So for now, I'm just gonna say that it doesn't matter. I'm gonna put it to do there. So let's go back and, well, the thing that we were doing before doing that stuff, we needed a way to get REX from the register stuff. So we have to go and fetch register operam, and we have to, well, no, even before that, because since we already passed back that, we cannot go and fetch the rm field there, so we have to get it directly, let's say, you know. So on the here, we want to fetch a register operand or a memory operand with the right byte, you know, which is gonna be on the rec field. So it's not like, I mean, this follows the idea that we have the rm and the rec. So we have to think a little bit of how to do that. We can, this has all the REX stuff, which we need, of course, because that's something we need. But we don't need necessarily the rec or the rm anymore. So the entry can tell us about that, see? So we're gonna say I mean, we can do it here, just with a lot more shuffling there. It's not like particularly crazy. Yeah. You know, there's just other flags passed away, you know. So we have to see later on, we have to compress all this stuff, of course, if we see a pattern. But yeah. So we can say we're gonna do the same stuff. So let's say and the thing we need to do is the same thing, isn't it? We just say that we're gonna have So I don't care about the RX right now. I just care about getting the right one. So we need to fetch the operand size, yeah. And for the operand size, it's gonna tell us. It's gonna tell us. It's gonna tell us about the thing. You know, we're gonna get the right thing there because we already encoded there. So this is good. Now the rec group type, we have to use it. You know, we have to define it somewhere. So we have to get this as well. Rec type, we have a GPR there, GPR64. We do the bit scan, and that's pretty much it, isn't it? And then we have the offset. Now we will need an offset here, which is this thing. And yeah, that's all she said. Now, yeah. Begin operand extraction. We need to go to tables, mnemonic entry. And of course, this is not gonna work, but forgot to say that we have to add this to the thing we have here. Now I think I'm gonna call them uh, another way to do it, it would be just to do this, and then we wouldn't need the state. Probably I like this more. So because we are like collapsing a lot of stuff here, and probably that's not what we want. And I think this is well, this is more like this. Well, it would be it would be the same, because at the moment when we, since get mnemonic entry anyway is moving past by the thing, you know, is only if we modify the way this offsets and moves the C by, then we'll get the thing. Yeah, well, then we will get like the information about the thing, you know. So that instead of doing this, well, I'm gonna do it like this. So because we don't need, I mean, now we see that we just don't need a moderate byte for making this kind of thing. We could, but I mean the main purpose of this is just to get the entry. You know? Later on we can just go and resolve. Now what we could do in that particular case is just say, well, this can get the entry and how you call this, mem buffer or rec buffer, sorry, and rec buffer count, which this can be another thing to do, you know. And it's like saying, hey, you know, probably you can pass me this and I can fill it with to you if that's the thing you want. I like that more, you know. And then the whole functionality, the whole functionality would be the same, you know. And then we'll need to do this. And I don't know why do we have a lot of this. I don't know if it was okay. And here we can say, well, we just print the instruction, you know, and print with the buffer being done. Now this of course have to, if it's gonna print the rec buffer and rec buffer count, is so yeah, something like that, I guess. And in fact, if we do it that way, we can just say that. Yeah. And here we just say, hey, you know what? Gotta fetch a register opener. And we need to pass, well, the effective operand size, fetch mother and by, fetch R and field. Which is data that we have here. So we probably wanted to have a structure, but I'm gonna do it without the struct before, and then I'm gonna collapse that stuff. Well, I'm gonna put it here. And that way we don't need to do this anymore. And that's okay, because yeah, I don't want to get huge with this if we don't need it. And for this special case, I think it's better we do it in line. So instead of having that overhead inside this call. So yeah, this, oh, what did I, oh my god. So this is, yeah, we're not gonna have the main abide, and we have the main abide. So let's change all the problems here. We can pass it here. And just say in fact, I can collapse this stuff into the other side. Yeah, just do it in line without all this overhead. So let me think if that's possible. Table REX, and then we can collapse that with compression oriented programming. Workgroup base, infill offset, rectable pitch. So yeah, I mean, we didn't need to change that at all. We don't need to call it. We just need to do this stuff. You know? You know what I mean? So I'm gonna put that onto here. We don't need that. Inline it, and then we say, you know what, we don't care about it. Then just say that. And then here we're just gonna say that and here menu bar is gonna be you know, now see by the pointer, that means we have to reference here. There's stuff the same. We don't have the operand size. And then we can pass the buffer size as well, I believe. Well, in fact, I mean, I don't know if we this is to have a pointer or to have the whole thing. It depends, because I mean, we can just give the thing back and fill it, and then you just play around with it. But since we are just using it back again, and it's like, hey, you know, the entry, so yeah, it's better the pointer here. Is that all? There you go. So we did a little transformation in there. We can just see what happens now. So we can fetch this thing, and we didn't set the rect filling size. Okay, it's important. There we go. Now we have it. The result, it's a push. Yes, it is. And the main of byte is 50. The offset is blah blah blah. Entry was not y. What do we have? Why is entry value? Oh, because we didn't find it that way. Okay, so my bad, we didn't change it, so we didn't finish this thing. This is now like this, and this is like this. Now we don't need this. And that's all we need. And then this is just the same, and this is the entry. Now I'm gonna call it out entry. So let's go in here. Now our entry rec type is GPR. Info bit scan reverse for the open size, that's 4. Oh, and and we need the other pass as well. I mean, it's not like particularly hard to think about it. It's just like, well, here we don't need these things nor these things. And then we can say where we have here no fetch register operand. Here we go. This right here is the thing we need. Now I don't know the case scenario, but we're gonna just keep it that way. And if we see that we can compress stuff because we don't need it, we can do it. But for now, we don't know if this. I mean, if this is if there's just one case for this. So we have register operand size. Then we have an effective operand size, you know, which, well, I'm gonna call it effective operand size. And here it's not this by itself, is more operating mode. Well, at least for the thing we have seen. Probably not. Probably we have two of them, you know, because operating mode, then well, this is the case for now, and later we're gonna fill the others, okay? There we go. We got REX for that particular cache, and we got that thing. Now I'll buffer account. We got REX. Okay, so we are not copied. Okay, yeah, my bad. Yeah, where is it? We're passing a pointer whenever we're passing the pointer of pointer, you know. So where is it? Entry. I'm gonna do it this way, I guess. Right now it's okay. Yeah, it doesn't matter. I mean, the only thing is like this thing, so we're gonna have like a copy of it, and we're gonna use a copy of it. Probably it's okay. Since we're not gonna use the other. I mean, we are not like refetching this stuff. Yes, we are, but I mean the memory referencing from here would go from the entry itself, copying it from the stack, so it's the same, you know. The only thing is that we are probably referencing from the stack, and then we are referencing from data from part, you know. So that was the problem I like to think about, but in any other case it would be the same because we don't know which part of the entries are more relevant. So they are just like the fetches on the entry that are the fetches on the ID thing and the system data information that we did that thing. So yeah, so I think that's better. And then we just now that probably means, well, that actually this is incorrect. That's what we want to do. So the entry has a copy of it. Okay. And we print the REX. Okay. That's alright, because well, we didn't say anything about the other information, so we're just pushing on REX, and that's all we got. What else? And cbyte, now it's pointing to 40, which is correct. So let's see if we print the other one. The entry is a move SPR REX. R20 REX times 2 0 0 0, etc. So that's correct. RVP, that's correct. And if we see here, we have it: push REX, move SPL REX, move SBX R13 REX times 2 0 0, move RBX RBP plus REX times 2 0 0 0, RBP plus REX times 1, REX times 4, SP R12 8. The other stuff looks pretty the same. We don't have any changes at all but the push REX stuff. Okay, so that's good. So let's copy this again, and well, just before doing that, let's see if we have time. Let's do the one with the push R13, let's say, yeah, which is, or push R8 we can do. It has 4150. Eight, 9, 10, 11, 12, so it's 5. So 50, 54, 51, 52, okay, yeah. So 54, it's R12. So we say that we can do the same thing and encode Now this is 54. That means that it, even though it's the same instruction, it has an offset there. Ooh. Okay, so that means that we add another entry, as we do normally. Or we have a way, I mean, yeah, I mean, the opcodes are more complex than just having entries that have different IDs, which it would be nice. It's just like, I mean, we are seeing like the whole thing, I mean, all requirements that the opcodes themselves need, and we just have to make sense of it. So that's kind of the quirky stuff. And yeah, so push here, let's say on the system we have right now, we will need to push another entry, so I'm gonna do that for now, and later we're gonna think about something different, right? Push entry 01. Is the same thing, but this has another encoding to look for. So probably the thing is that, well, yeah, because these are special cases, so we will need to have like 7 thing. Well, just well, that makes sense because on the entry you have it that way, on the entry you have the things explicitly done that way. We have a complete row of different encodings for the same instruction, which they do have the same thing, but the only thing is that they just occupy the whole thing. And normally, I mean, this is the first time we find that this thing, so I mean, I see that it's the common case here, so yeah, I mean, that's the way to go. So push entry, probably we need better names than push entry 01 stuff, but for now it's gonna do the work. I'm gonna say 0x54, and we're gonna add here so let's see what's gonna happen. Of course, we haven't done the thing for print out correctly this stuff, but let's see what happens. We get an out entry, which is a push as well. I don't know if we are looking at it should be the other one, but since it's a copy, that's the problem. We don't want copies, of course, but for now it's just gonna be okay. Rec type, rec group, rec type GPR, rec group type, rec type GPR 64. operation mode 64-bit, data size 32-bit, rec groups, out entry, rec type. So the C byte it's 50, minor byte is 54, that's correct. And we just do the same stuff. We're gonna get RSP instead of R13 because we didn't change the ID. So let's go and do that, and that's pretty much it. So get mnemonic entry. So now we're gonna do this, and we need the REX by, and we need to say system stay fetch register operand. We need to say that we need also this. We have to get the RX fields somehow. From the RX byte, and then we don't need this, we don't need that, we don't need this, we don't need that, we don't need this, we just need that. For XP, we set some state records rectype GPR64. And the is the thing we had before. Yeah. And this is the same. We need to do this as well because so we have an offset and we have an info offset. So we just can say get RX fields. Info offset equal info offset greater than equal 4. So we just need to pass REX by now. So we're looking at 41. That means we have an REX without W. Then we go inside here. We say, well, you know what's going on here? rec field inside. We now have that effective operand size, and here we have the info. We got the REX. The REX pretty much just has the base. We changed to VPR64, and we have our 12. There you go. Push R12, that's correct. Zip byte is 50. This is another push. Push REX. And the other stuff is just the same. Push R12, push REX, move SPL REX, blah 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 blah. REX is 2, 0 0 0 0 FF1 4 12 times 8 12 13 REX blah 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 REX blah 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 RDX REX FF0 OP ST0 ST1 ST1 ST0 0 0 0 4 being resumed line RX71 8x3 X1. Yeah, so yeah, that's pretty much it. And we can run it as many times as we want. Yeah, so that's for using REX registers and rec fields inside minute bytes, which is something special if you think about it. And I mean, that's useful in the sense of optimization, because the less size of the byte, I mean the less size of instruction encoding, the faster the processor can make sense of it, you know, can translate it and decode it. So yeah, I mean that would be great if all the instructions could be that way, but of course that's not. And we haven't got even to EVX. That's where all bananas and sizes grow to 15 probably, or something like that. But yeah, I mean even the size gets respected, and even, well, I don't know if, yeah, I mean the limit should be 15 bytes, which I don't know, we have to wait. We have to wait to see that. Alright, so yeah, so that's it for today. I can even say, I don't know, push SPL, which is the thing that works in there. No, how it's called? No, but we cannot. Well, we cannot push. We cannot push SPL1. You know. We cannot push. Yeah, we cannot. We don't have that encoding because the effective operand size it defaults to 64 or 32. That's all, or 16 probably. But right now we don't have anything about 16. But yeah. So yeah, I was like thinking, well, we're gonna encode that. We kind of, yeah, the thing that we had before. We could, it wouldn't be possible to push SPL because it's an 8 thing, you know. So it's 8 bits. We can only push 16, 32, or 64 with instructions that we already have. So yeah, probably with others, probably it's a different story. But yeah, that's all she said. So please, if you have any questions, post them on Twitter or YouTube, and I'll be there to answer. Alright? Please make your questions related to the thing we did today, and I'll be happy to answer them. Yeah, I would say thank you very much for coming, and I will see you all on the next stream. Take care.